Hello, going to look at the Railsback curve, and we're going to look at how the first partials and the pitch can be determined by so-called modern methods using digital computers rather than analog equipment that was used originally. Here's the famous Railsback curve, and it's plotting the deviation from equal temperament versus the key number. So down here at A0, this curve here, which is the average of about 19 pianos that were freshly tuned, A0 is about 60 cents flat relative to the equal temperament, which is this zero line. And then, for example, up here at C8, it's about 30 cents sharp relative to equal temperament. And this green line is kind of a rough, or actually a very smooth approximation to this jagged curve. So in general, this curve is saying that the low number of keys are tuned flat and the high number of keys are tuned sharp. And this is from the abstract of Railsback's paper, 1938, basically repeating what I just said, with an additional comment about the chromatic stroboscope, which is the device that apparently Railsback used. This is from the 43 article by Shook and Young, and makes some more comments about how a microphone and an octave band pass filter and a chromatic stroboscope were used. In any case, we're going to test this hypothesis that the low numbered keys are purposely tuned flat and the high numbered keys are tuned sharp. And we're going to use a high resolution Fourier transform based spectrum to locate the first partial. And then we're going to use the autocorrelation to find the pitch of each key. And we're going to use MATLAB scripts to do that. Okay, the pitch is determined by finding the time lag of the first and strongest peak in the autocorrelation plot. And if this time lag is in milliseconds, then the pitch of the pitch frequency would be obtained by dividing that time lag in milliseconds into 1,000. Okay, here's a result of the study. We have up here in this first graph the location of the first partial as determined by this digital technique. The dotted black line here is the zero, which means zero deviation from equal temperament. Down here, the curves for the various pianos. I have a Steinway, a Kanabi, another Steinway, and a Yamaha P120. The last one is a digital piano, but its samples come from the Yamaha CF3S, which is a concert grand. Okay, now look at, for example, here is this purple curve is the Yamaha. You can see it starts out flat, and then it comes up, and it's above the black curve mostly, and then it comes up here and it's sharp. So it follows the overall Railsback trend. Down here, this blue curve is the Kanabi. Looks like the first one, area is on the order of equal temperament. In other words, it's right on, but then it quickly drops down to be flat for other keys. And it stays pretty much right near the black curve all the time. Up here, it's sharp. Now, down here, this is the plot of the pitches as determined from the autocorrelation. And here is the black overall Railsback curve, same as this curve up here. And you can see that for the low numbered keys, the pitch is pretty much on equal temperament. For example, this blue curve, which is the Kanabi, pretty much within 10 cents of equal temperament. And then until you get up here to the high numbered keys and it gets sharp. At the other extreme, here's a Steinway D that's about 10 cents sharp across the board or across the keyboard. And then it gets sharp too, up at the high key numbers. Okay. So the first partial traces are consistent with the shape of the Railsback curve, but the pitch is not for the low numbered keys, but it is for the high numbered keys. Now, why is this? Well, let's take a look at the low numbered keys first. Let's take a look at C1. C1, here's the plot of the line spectrum for C1, power along this axis in decibels, and then frequency along this axis. I've only gone up to 1,000. And you can see there are a lot of partials, there are about 30 partials here. And the pitch depends on the location of those partials and how they are related to each other. For example, we start down here, it looks like at the first harmonic, which is this red dotted vertical line. Let's see. I guess you could pick that peak as being located at the first partial. It's almost 50 dB down, and it's pretty close to the first partial, to the harmonic. Then we have the other partials being closer to the harmonics and more and stronger. For example, here the eighth one is weak because that's the string is struck at 1/8 of its speaking length. But then as the frequencies increase, you start to see the partials get sharp relative to the harmonics, more so, until out here, the partial is sharp relative to harmonic. Here's the partial, and here's its harmonic. It's sharp an amount equal to the fundamental, which is 32.7 hertz. The point, though, is that because there's so many partials, there's a lot to work with, and the pitch turns out to be, because of the separation of the partials, right around 32.7 hertz, as compared to where the location of the first partial is. Now let's take a look at the case for the high numbered keys. Different story. Here I'm plotting the spectrum of C8, power versus frequency, and going all the way up to 10,000, which I think is out of the range of hearing for most people. But you see, you really only have about one partial to work with. The second partial, which probably is this guy here, is 40 dB down. So you only have one partial to work with. So the pitch and the partial are pretty much going to be the same. And that explains why up here in this area, the pitch follows the Railsback curve, but it doesn't over here because there are so many partials to play with. And it turns out that the pitch is pretty much on equal temperament for the low numbered keys. So it looks like the pianos are not tuned flat at the low end of the compass, but they are tuned sharp at the high end. Okay, thank you for listening and watching.